The Earth acts like a great recycling machine. All the atoms, all the molecules are used over and over again as the sun's radiant energy and the Earth's inner heat drive the movement of atoms and molecules from one reservoir to another. In Lecture 41, I'll focus on the atmospheric cycles of weather and climate, which are driven by the sun's radiant energy. The outline of this lecture is straightforward. After reviewing the nature of cycles in general, and the water cycle in particular, we'll look at the atmosphere. Now, we commonly talk about the atmosphere in terms of its short-term variations, or weather, and its long-term variations, the climate. To do this, we need to consider 5 atmospheric variables: temperature, air pressure, humidity, cloudiness, and prevailing winds. In the last third of the lecture, I'll consider some of the factors that influence global climate and its variations. In this lecture, as in the last, we're exploring Earth's great cycles of water, air, and rock. Recall that all cycles involve 2 kinds of information. First, you need to account for all the reservoirs, all the places, for example, that water is stored in or that gold atoms are stored in. And then second, you need to think about the ways that materials move from one reservoir to another. Water moves by evaporation, by rain, by gravity. Gold atoms may move by hydrothermal processes or by human intervention, mining gold from one place, depositing it into bank vaults, into jewelry, and so forth. In talking about geochemical cycles, we focused on 4 shared characteristics. First, all cycles involve movements of matter from one reservoir to another. Second is that all these cycles are driven by energy, either from the sun or from the earth. All of these cycles, third, can be affected by human interaction. And finally, all of the cycles are interrelated. Now step back for a moment and think about these cycles in the context of the great principles of science, the great principles that we've been talking about throughout this lecture series. First of all, every physical system, including Earth's cycles of materials, must obey the natural laws. Atoms, for example, are conserved. So, for example, the total amount of water on Earth is constant. We know that if matter moves, then a force must be involved. So what's the force? Well, the force of gravity causes liquid water to run downhill. It causes water vapor to mingle in the atmosphere, but we also have the electrostatic forces that involve chemical reactions between atoms as well. So forces are always involved. You have to have a source of energy to exert a force over a distance, and so we have heat energy from the sun. We have also the Earth's inner heat, which can provide energy to move materials. We've noted that energy can change from one form to another. So the heat used to evaporate water, for example, is converted to the gravitational potential energy of rain and then of water in high-up reservoirs, and then that water can be converted to electricity through hydroelectric dams. So the first law of thermodynamics is very much a part of looking at geochemical cycles. We also know that heat has to spread out in accordance with the second law of thermodynamics. So oceans transfer heat across the globe, bringing warm water from the equators to the north, bringing cold waters from the north in deep currents back down to the equator. Well, let's see how these same principles can apply to the great cycles of air and of rocks. The Earth's envelope of atmosphere contains gases hundreds of kilometers thick that surround the planet. Now, at first glance, it might seem odd to speak of an atmospheric cycle. After all the atmosphere appears to be one continuous mass of gas, of air, rather than several discrete repositories like the lakes and the rivers and the oceans that we've been talking about. But at any one time, the atmosphere can be divided into separate air masses. Now, each of these air masses is more or less uniform in its properties, and each air mass can be thought of as a separate air reservoir which has distinctive properties from the adjacent air masses. At times, there are adjacent air masses that occupy different regions close to the ground. So, for example, you could have a low-pressure system in the Midwest while there is an adjacent high-pressure system in New England. and those would be two adjacent air masses. It's also possible that air masses could represent layers of the atmosphere. So, for example, you could have the troposphere near the ground, the higher up stratosphere, as being two masses of air that have separate properties and therefore behave, in a sense, as separate reservoirs of air. In order to understand the properties of air masses, we need to define two closely related terms. And these are the weather and the climate. Weather, that's the state of the atmosphere at a given time and place. And so at any given time, at any given place, you can define the weather, and it's influenced by lots of factors that are variable from day to day, not to mention from season to season. Now, there certainly are places where the weather can be fairly consistent. If you go to the desert southwest, you can expect hot, dry weather. If you go to Santa Barbara in the summertime, you can expect somewhat cooler but also quite dry weather most of the time. But New England, the weather can vary on a matter of day to day and hour to hour and minute to minute, it would seem, as different fronts come in and different air masses collide and different amounts of humidity and cloudiness prevail in the region. Climate, on the other hand, is a very long-term average of weather for a given region. A regional climate, of course, can be hot or it can be cold, it can be wet, it can be dry, and the weather on a given day can be quite different from that average long-term climate. And yet we do see long-term patterns that persist for decades, for centuries, even for thousands of years. On the other hand, for reasons we don't quite understand, it appears that at times climate can shift quite rapidly. So an area that was hot and dry can become much cooler and wetter, or vice versa. And that's a great area of research, as we'll see. Why do climates change the way they do? There are 5 variables that define the state of the atmosphere. And these are the key to understanding both weather and climate. We have temperature, air pressure, humidity, cloudiness, and prevailing winds. And your local weather report typically covers all 5 of these variables. If you listen carefully, you'll hear some description of all of those. So let's go through these 5 and see a little more detail how they behave. First is the temperature. The temperature is reported in daily weather predictions, and that refers to the temperature at ground level. The range of temperature is huge on the surface of the Earth. The highest average daily temperature is 94 degrees Fahrenheit at the Denakil Depression in Ethiopia. The coldest average temperature is minus 70 degrees Fahrenheit at Plateau Station in Antarctica. Temperature always varies strongly with altitude above the ground, and indeed this fact is used to define the major layers of the atmosphere. You need only consider the first 2 layers in this lecture series, although scientists have defined many layers of atmosphere and lots of detailed sublayers and so forth. We're not going to get into all that, but we are going to look at 2 of these, the troposphere and the stratosphere. The troposphere extends up to 10 kilometers to 16 kilometers, depending where you are on the globe's surface. It's defined by a zone of decreasing temperature with altitude. So as you go higher and higher, say you go in a hot air balloon and you go higher and higher, as long as the temperature is getting colder, you're still in the troposphere. Air near the ground, by the way, is heated. It rises, and as it rises, it cools because it expands slightly. Thus, the troposphere is much thicker near the equator, where it's warmer, than it is near the poles. And that's why you have this variation. Near the equator, the troposphere is perhaps 16 kilometers thick. Near the poles, it's more like 10 kilometers thick. The second layer up in the atmosphere is called the stratosphere. It extends up to about 50 kilometers. And the temperature in this zone, surprisingly enough, increases, often by as much as 50 or 60 degrees centigrade with altitude because of their small quantities of the gas ozone. Now, ozone is a gas that absorbs ultraviolet radiation from the sun. So the higher you go, the more this absorption takes place. And therefore, from the base of the stratosphere, 10 or 16 kilometers up to about 50 kilometers is a zone where temperature gets higher and higher and higher the higher you go in the stratosphere. Okay, the second variable, that's the atmospheric pressure. Pressure is defined as a force acting on an area, a force per unit area. And atmospheric pressure represents the weight of air that's above us. We have a column of air pushing down on all of us, squeezing us from all sides. And at sea level, that's at about 14.7 pounds per square inch. Air pressure decreases quite significantly with altitude because air is compressed by its own weight. So the higher you are, the less air there is above you and the less weight there is to push down. If you go up to a height of 5.5 kilometers, and that's far below where commercial jetliners fly, you find that the air pressure is about half of the value at sea level. And if you went up to 32 kilometers, which is much higher than commercial jetliners, the pressure is only 1/100th of that at sea level. Pressure also varies laterally. That is, you have regions, air masses, that tend to be at higher pressure or at lower pressure. And the reason this is true is quite simple to think about. Air tends to pile up, just like any fluid would. If you have a circulating air mass that's going around, at the center of that circulating air mass, the air is being pulled outward by centrifugal force. So there's a low pressure area. But regions at the boundaries of that experience the high pressure as the air piles up towards the outside of one of these rotating masses of air. There's another phenomenon. Air in low pressure systems tends to rise up. And when you rise up air into the cooler regions, you tend to get increased clouds because the water starts condensing out as it gets colder and colder in the air. And so low pressure areas tend to be more cloudy areas. Indeed, they tend to be much wetter with more rain. By the same token, high pressure areas tend to feature warmer, drier air. You can get a very significant air pressure difference at the boundary between the thicker equatorial troposphere and the thinner polar troposphere. Recall we said that the troposphere, the layer closest to the Earth, is much thicker at the equator. It's thinner in farther northern latitudes. And because of this, there's sort of a slope in the troposphere-stratosphere boundary. And right at that slope, you can actually have very large changes in air pressure, which causes a high-speed jet stream at the troposphere-stratosphere boundary. Across the northern North American continent, this jet stream tends to run from west to east. That's why it causes flights from New York to LA average about 1 hour longer than jet flights from LA to New York. It's because of this jet stream, which is the result of the changing thickness of the troposphere and the pressure difference caused by that. Okay, the third atmospheric variable, that's humidity. That's a measure of the atmosphere's highly variable water content. Now, let's talk about the composition of the atmosphere. The bulk composition of the atmosphere is remarkably uniform around the globe. It contains primarily two gases, that's nitrogen and oxygen. And those two gases make up 99% of atmosphere that has been dried, that has had its water content taken out. Nitrogen, in the form of N2 molecules, is the most abundant constituent. It's 78% of the atmosphere's volume. Now, remember, N2 is a covalently bonded molecule. It has two nitrogen atoms that are bonded covalently with a triple bond. That's a very strong, very durable, long-lasting molecule. The nitrogen content of the atmosphere apparently has been fixed for a very long time because of the inertness of this molecule. The other gas, oxygen, is O2. It's a molecule that accounts for 21% of the atmosphere's volume. And recall that oxygen has a double bond between two oxygens as a covalently bonded molecule with two oxygens. But this is a very reactive gas. It readily takes part in oxidation reactions. So oxygen accepts electrons, recall, for example, from carbon or from iron, from hydrogen, to form oxides. And if left to itself, atmospheric oxygen would quickly be reduced to nothing because it would react with surface chemicals on the ground. However, oxygen is constantly being replenished by plants. So plants play this essential, vital role in the atmospheric cycle, putting oxygen back in as it's used up. Now, many scientists argue that the discovery of another planet that has an oxygen-rich atmosphere would be an absolute, incontrovertible sign of life for just this reason. The atmosphere also contains a number of minor elements. It contains a small amount of the inert gas argon. That's about 1%. Now, argon is element 18. It has a completely filled third subshell of electrons, and as a result, argon is this inert gas. It floats around the atmosphere as individual isolated atoms that don't bond to anything. It took a long time for argon to be discovered because of its inertness. Following argon, you have about 35,000% carbon dioxide in the atmosphere, just a very small amount, but a significant gas nonetheless. And then there are traces of a dozen other gases in the atmosphere. Some of these trace gases, such as ozone, can reach unhealthy levels in regions of high air pollution. So we constantly monitor the composition of the atmosphere for this reason. Okay, now to water vapor and humidity, which is the variable we're talking about here. The atmosphere always contains some water vapor. Though the amount is extremely variable, it depends on temperature and it depends on relative humidity. Air on a very cold, dry winter day can hold less than 0.1% of water by volume. And think on a very cold, dry winter day how dry your skin feels, how your lips get chapped very easily. That's because there's so little water in the air and water is constantly evaporating from your body into the atmosphere. On the other hand, on a very hot, humid summer day, air can contain several volume percent of water. This is why in monsoon season in tropical areas, you can have torrential rains for day after day, hour after hour, pouring buckets of water down. The atmosphere can hold that huge amount of water in very hot, humid weather. Okay, the fourth variable is cloudiness. And this, of course, is a variable that's very closely tied to humidity. Clouds represent a concentration of tiny water droplets, or ice crystals. These substances scatter light, and so they appear white to us in the atmosphere. Clouds form when air becomes saturated with water. And that's a process that often occurs when a mass of air rises in the atmosphere and then cools down. And that's very commonly a way that you form clouds. You'll often see clouds dramatically outlining the contact between two adjacent air masses. Sometimes you'll see a layer of clouds at the boundary between the troposphere and the stratosphere, a high layer of clouds, for example. And sometimes you may see a band of clouds on the horizon marking a front, an approaching weather pattern, for example. And this is where two air masses of different temperatures collide. Now, common examples of the dramatic anvil-shaped clouds, the thunderhead clouds that occur when a warm air mass collides with a cooler air mass. And I want you to think about what happens when a warm air mass hits a cool air mass. The warm air mass is less dense. It rises up on top of the cooler air mass, and that warm air mass also probably has more moisture. As the warm air mass rises up and cools, that's when you get cloud formation. That's when you get the precipitation of water droplets, and you get these huge rising thunderhead clouds, the great anvils in the sky. This increase in elevation, it cools the warm, wet air. It causes clouds. It causes rain. Great turbulence, which also causes lightning, you recall. Strong winds. That's all part of this contact between two air masses of different temperature and different humidities. Now, clouds and rain often form on the windward side of mountain ranges. This is, once again, where air mass is forced to rise up over the mountains. This is a very dramatic phenomenon. This occurs, for example, in the Hawaiian Islands. In the big island of Hawaii, you have air masses coming in from the east off the Pacific Ocean. These are fairly warm, fairly humid air masses, and they hit the Great Mountains. And then the air mass is forced to rise up over the mountains, and as they do so, that precipitation comes out. And you have intense clouds, intense precipitation and rain activity on the windward side of the island. In some places in Hawaii, well more than 100 inches of rain per year. But just a few kilometers away, on the far side, on the western flanks of that mountain, you have a dry and arid climate because the air has lost its moisture on the up side, on the windward side, and then as the air pours over the other side, it cools, it warms up and it's dry. And so it no longer has any moisture to precipitate. So, for example, on the Kona side of the big island of Hawaii, you have beautiful, dry, warm temperatures most of the year, where just a few kilometers away it could be pouring rain all the time. Now, the fifth atmospheric variable is the direction and the strength of winds. Winds are a consequence of atmospheric convection. That's a process that helps redistribute Earth's heat. And one of the easiest ways to think about this is the ocean breeze that you experience on a tranquil summer day. Now, during a sunny day, the land heats up. The land heats up a lot faster and a lot more than the water does. So warm air rises from the land on that hot summer day. And as a result, the cooler air coming off the water has to replace it. And so during the hot summer day, you get a sea breeze, a gentle breeze coming in off the water where that air is just replacing the air that's rising up over the land. In the evening, as the land cools, and often cools more than the water, the pattern reverses, and the warm air can flow up from the water and off from the land, so then you get a landward breeze during the evening hours. On a very much larger scale, the same thing happens with the equator and the sun. The sun heats the air around the equator more than at the poles. As a result, the air rises from the equator and basically circulates towards the two poles. If the Earth did not rotate at all, then you'd just have a weather pattern where you had prevailing winds in the high elevations from the equators to the poles and along the surface from the poles down to the equator. But in fact, the Earth does rotate, and this shears, it spreads out the weather patterns, so you have prevailing winds from the east and to the west. This motion divides the atmosphere into bands. You have ships, for example, that sailed from Europe to the Caribbean on the northeast trade winds, and then they returned on the more northerly route using the prevailing westerly winds. The similar situation we've talked about in the banded atmospheres of Jupiter and Saturn, where you also get very rapid shearing of a huge atmosphere under the influence of the rotation of the planet. Well, so far we've been talking about the weather, which is a short-term variation of the state of the atmosphere. But what about longer-term changes? That's the climate. Now, climate seldom changes much on human timescales. But there's new evidence to suggest that the Earth may occasionally experience short periods of dramatic climate change. By some estimates, we're now in the middle of such a period of rapid global warming. Climate change research is thus a very hot topic. We have year-to-year measurements of global temperature, and in recent years it seems that the Earth is getting warmer at an alarming rate, perhaps several degrees per century. The average global temperature is extremely difficult to measure. But the 15 hottest years on record have all occurred since 1980, and 1998, the most recent year that's been surveyed at this point of this lecture, is by far the hottest year since records began being kept in the 1870s. It was 1/4 of a degree warmer than any previous year. Now, long-term sites of weather stations have become more urbanized, and so you have to worry about things like heat island effects. As you urbanize a weather station, more and more concrete, more and more asphalt, the area tends to get warmer. It just absorbs more sun's heat. But there are many other ways to get around this. You can make satellite measurements of global temperature. You can measure the average temperature of the water from satellites and so forth. And while these measurements are difficult, it now seems to genuinely indicate that the globe is getting warmer by all different measurements. By the most optimistic estimates, the global average temperature is going to rise at least 2 degrees centigrade by the year 2100. And there are other estimates that are at least 3 times that. Such a climate change would induce a significant increase in sea level. It would cause a shift in agricultural lands much farther to the north. So some of the fertile areas of the Midwest would become dry and difficult to farm, whereas there are new areas in Canada that would suddenly open up as agricultural areas. Well, whatever the cause, we have to learn more about the factors that affect climate. And an important new scientific discipline in this regard is called paleoclimatology. This is the study of ancient climates, which are revealed by a whole variety of evidence. You can, for example, look to fossils. Fossil plants and animals that provide essential clues. Fossil pollen grains, for example, reveal the distribution of plants and the kinds of species, the ones with distinctive habitats. Fossil corals can indicate the regions where there were coral reefs and warm water. You can also look at rock types. Glacial deposits, for example, indicate that there was glaciation and ice ages in a region. One of the neat ways that people do paleoclimatology is through ice cores. You can get ice cores in Greenland and Antarctica, and some of these hold a continuous record of more than 100,000 years, year-by-year records of ice deposition. And they hold records of the atmosphere in the concentration of tiny air bubbles that are encased in the ice. Now, it turns out that you can determine air temperature from these air bubbles because of the ratio of the lighter oxygen-16 isotope to the heavier oxygen-18 isotope. That's a very sensitive indicator of temperature. As you see, the warmer it is, the easier it is for the heavier oxygen-18 to enter the atmosphere. And so a high O18 value gives you a higher average global temperature of the atmosphere. Now, the ice core climate record seems to indicate that dramatic temperature changes can take place in very short periods of time. Both in Greenland and in Antarctica, there are places where there was a 10 to 20 degree temperature change. This is 10 to 20 degrees centigrade temperature change in just a few decades. For example, at the end of the glacial advance about 12,500 years ago. Some scientists suggest that this event was caused by a rapid rise in greenhouse gases, perhaps released from the ocean. Carbon dioxide is another possibility. Carbon dioxide from volcanoes might be the culprit, or methane. Methane, which is also trapped sometimes in the pockets of the ocean floor. Now, we're going to examine the greenhouse hypothesis a lot more in lecture 59, but this is an important area of climate study. The fact is, we don't know what has caused the drastic, sudden climate changes, but we do know that a similar rapid warming today could have catastrophic effects on the world's ports that are near sea level, on our agriculture, and on many other aspects of civilization that we take for granted. Well, let's shift gears now. Think about climate in terms of plate tectonics. One of the most intriguing aspects of climate studies is a growing realization that there's a strong link between climate and plate tectonic processes. The climate of a region is profoundly affected by details of the distribution of landforms and bodies of water. And you're all familiar with this. That, for example, you could have an ocean current that takes warm water from equatorial regions to areas, for example, Great Britain, where it's much, much warmer. You can have a Great Lake, and if the airflow is across that Great Lake in the wintertime, you can dump buckets of snow on places like Buffalo, New York, and Ithaca and Syracuse, New York, just because of the presence of that lake. A mountain range can cause intense changes in climate as well. You can have some regions that are extremely dry because the mountain's blocking passage of wet air. Other areas, as we saw in Hawaii, that are extremely wet because the mountain is in the way and intercepting wet air masses. Even the position of continents, whether there's a continent on a pole, determines much about the climate of the globe. Some fascinating changes in climate are the result of currents. For example, the California current, which takes cooler air from the Bering Sea area down along the California coast, moderates the climate of California in quite a dramatic way. We also see the production of hurricanes as another consequence of the position of oceans and continents. That's the consequence, of course, of plate tectonics. You get hurricanes that obtain their energy from the water in equatorial regions. So when the ocean is much warmer than the air temperature, you get these cyclonic patterns developing. Therefore, the position of oceans and the position of continents is critical to the formation of hurricane-like storms. Now, the idea of mountains affecting climate is one that's quite intriguing and has led to the proposition of an amazing engineering project in China. And it's not clear that this will ever happen, but there's a great mountain belt that runs east to west across central China. And this mountain belt, in a sense, wreaks havoc with China's climate. Air masses that come from the south run into this mountain belt and dump huge amounts of rain south of the mountains. This causes flooding in central China. It displaces many people, it disrupts agriculture, and causes great hardship. At the same time, just north of that mountain range, there's a vast desert area. A desert area that is comparable to many of the main provinces of China, but which are unusable. You can't grow anything, you can't live there because of the dryness. Chinese officials have actually proposed that over a long period of time, using perhaps millions of workers working for hundreds of years, you could level a portion of that mountain range, opening up a passageway so that air masses could now flow through the mountain range, providing moisture to the north and reducing the flooding in the south. It's an amazing idea. Perhaps only the Chinese could come up with such a grand and glorious scheme, but it's one that does challenge the imagination. It's an amazing example of how physical features on the Earth affect climate. Well, to summarize this lecture, we focused on two aspects of the atmosphere. First, we looked at the short-term cycle of variations of weather, and then the long-term variation of the climate. We've seen that the state of the atmosphere, both for weather and climate, is defined by 5 variables. We have temperature, air pressure, humidity, cloudiness, and prevailing winds. We've seen that the climate can vary over long periods of time as a result of changes in atmospheric composition and because of the positions of ocean currents, landforms, mountains, and so forth. Ultimately, then, the global cycle of water and of air are tied to the great cycle of Earth's rocks, the solid Earth cycle, which is the subject of the last lecture in this series on geochemical cycles.